Okay, so in this part of the experimental techniques lecture videos, I'm going to go and talk about the process of sampling. So this is the process where we make sure that the measurements we're taking are actually capturing the data we want to capture. So there's lots of different schemes for actually doing the process of converting a voltage, analog voltage, to digital numbers. And I'm not going to go through exactly how all of those work. This is not an electrical engineering course, but there are some common parameters we can go and talk about. So we can talk about the input range. So what's the biggest voltage you can measure? And typically those are 1, 5, 10, or maybe 20 volts. So generally speaking, it's a sort of number of volts of signal is the range you work in. And then we might want to talk about the resolution, which is the smallest difference in voltage you can measure. And again, there are various ways you might want to talk about that. You can specify it in terms of a number of digits, you can specify it in terms of a number of bits, or you can specify it in terms of a number of number of levels you can distinguish. So the table below shows a way these sort of convert between each other. So inside the computer, you're representing the number as the voltage as a binary number. And a binary number has a number of bits, and that scales straight forward to the number of different levels or counts that you can go and manage to have. So, and then you can think about how does that relate to the number of digits of resolution when you write out the number as a conventional decimal number. So it's kind of cheap and cheerful meters. We're maybe working at 3.5 digits, meaning you have 99.95 and then 99.90 sort of numbers. And if you look on the table in this slide, then you'll see that that's somewhere between 10 and 12 digits, sorry, 10 and 12 bits of information, which is giving you somewhere between 1,000 and 4,000 actual levels you can measure in. Whereas on the other hand, the sort of instrument we tend to use for sort of research measurements tends to be either 5.5 or 6.5 digits or even more. And there you can see we're looking at up to somewhere between 18 and 20 bits of data. Quite a lot of measurements also work on 16 bits, which you can see is around about 5 digits worth of precision. And then very high-end instrumentation will go up and use 24-bit digitization. So in other words, that's getting sort of 7.5, heading towards 8 digits of information. So those are the sort of numbers we go and talk about. And on the other hand, you might want to talk about the sampling rate. So that's how fast can you repeat a measurement of the voltage. And that's typically quoted in terms of samples per second, or possibly samples per power line cycle. So, because the instruments are all often designed to work on either a 50 or a 60 hertz mains power supply, and so you talk about how many measurements do you do per power line cycle. Alternatively, you might talk about the bandwidth of a measurement. And very generally, there is a trade-off between resolution, sampling rate, and cost. And then finally, you want to think about the accuracy. So what's the difference between the voltage you measure and the true voltage? And now that ends up being a combination of many factors. So things like the resolution, obviously, but also calibration of your system, and as well as noise, and also factors involving the sampling rate. So the challenge you're facing is to think about what is the combination of resolution, of accuracy, and of sampling rate that I need in order to go and do my measurement, because there's no point maxing things out and it just drives your cost up for no good purpose. On the other hand, if you don't think about what you need, you can easily end up doing the wrong measurement or not measuring what you thought you were measuring. So let's look at an example then of working out what is the bandwidth or the sampling rate which you actually need to go and achieve in order to go and do a measurement. So here we have a complicated signal that is just about periodic, but it's got a very, very complicated waveform. So I don't know, this might be some kind of biological signal, or maybe it's some kind of vibration spectrum, who knows, but it's a signal that's varying over time in quite a complicated way. And we want to go and measure something like this. So what we can do is we can go and take periodic measurements. So we just go and sample that voltage every so often. And you get a series of data samples. So the black dots here represent where we've done a measurement. And then the question is, well, are we measuring the black dots often enough in order to be able to go and see what the signal really looks like? And it should be fairly clear from this picture that we're not really going to do that, because if we just join the dots between the black dots, then the red signal is what we'd measure. And whilst it's got some features that resemble the actual true blue curve, we're missing quite a lot of things. So we're not really picking up as much detail in the signal as we might actually want to go and see. And we're assuming here that we're able to go and do these measurements very, very fast. We're going to get an instantaneous measurement. And of course, that's not always true either. So if instead of measuring just on the dot, you were measuring some kind of average over a period of time, then again, that would also go and change the signal you measured quite remarkably. Okay, so the question is, how fast do we need to measure in order to get back the signal that we wanted to go and do? And this is governed by a thing called the Nyquist-Shannon theorem. So Nyquist-Shannon theorem tells us that the minimum sampling frequency So the question comes then, what's the minimum rate at which we need to go and sample our signal in order to guarantee that we're going to get enough measurements to be able to reconstruct the signal? And this is something which is given by the Nyquist-Shannon theorem. And it says that if we have some frequency, which is the highest frequency we're interested in looking at, then we need to sample it at 2 times that frequency in order to ensure an accurate measurement. And if we don't go and do that, then we can end up with an effect called aliasing. So here's an example of where aliasing would be a problem. So imagine that we're not able to sample our signal particularly rapidly. And so we're only sampling at a much slower rate than the frequency we're interested in. And now we go around and try and join the dots. And even if we assume we join the dots with a nice sine wave, you'll see that the red signal we've joined up here is at a much, much different frequency from the true signal we're getting at. And in fact, the signal that we reconstruct is given by the beat frequency between the signal we're measuring at and the signal that we're interested in looking at. And then you can understand why it is that we need to go and twice the frequency that you want to measure, because the beat frequency is the difference between the measurement you're interested in and the frequency at which you're really sampling it. So the aliasing signal means that as we get closer and closer and closer to the frequency we're sampling at being the same as the frequency that we're trying to measure, then the closer and closer we get to looking at the red curve, which is actually going to measure just a flat line. If we then go past that, then we start being able to get a beat frequency, which you can see again. And if we go to the point where we're sampling twice as fast as the signal we're interested in, then the difference is going to be the frequency we're interested in looking at. So in other words, the beat frequency we pick up is the same as the frequency we're interested in measuring. And that's why Nyquist-Shannon theorem says we have to go at least twice as fast as the frequency you actually want to measure.